Welcome back. We'll discuss this experiment 4. Here we have to do this 4-bit adder cum subtractor using 1-bit full adder. So it means same circuit is going to behave like a adder and a subtractor. Let us see how it is behaving. So what basically, addition is, that 4-bit, right? So let's say you have A, 4 bits, 1, 0, 0, 1. And B is having, let us say, 0, 1, 1, 0. Addition is very simple here. We just perform bitwise addition here. 1 plus 0, 1, 0 plus 1, 1, this 0 plus 1, 1, 1 plus 0, 1. So that's how you perform. So in case you want to perform subtraction here, A minus B, then subtraction is nothing but adding 2's complement here. This is the minus, right? This is minus B. So negative number is represented in 2's complement. So if we are adding like this can be written as A plus inside the parenthesis you can write like this. A plus inside the parenthesis minus B. This minus B is a negative number. So we have to take the 2's complement of this number. So how do you take the 2's complement? You first complement this entire number and then you add plus 1 to that. So it means complement of complement of this B is nothing but B1. And adding 1 to that will give us 2's complement, right? This 2's complement. And then this is the addition. This addition is what you are doing here. So subtraction, how do you do the subtraction? You add the 2's complement number. The second number of that 2's complement you take. And you perform the addition with the first number. So that will give us the difference. So that is the subtraction. Okay. So that's how this is performed. Now to do this one here, to perform the addition operation here, we straight away take A plus B. But to perform A minus B, what we take? We take the 2's complement of the second. And then we perform the addition. So, like this it is. In first case, if it is an adder circuit, simply A plus B. If circuit has to behave like a subtractor, then A plus 2's complement of the second number. So in both cases, addition is common. So that's why we use adder, but with this technique. So let's see how this technique is applied. So if you talk about the XOR gate, if you take the XOR gate has got 2 inputs, A and B. A and B. And the output is Y. So let's take this AB values. 0, 0, 0, 1, 1, 0, 1. And the output is, for 0, 0, output is 0. For 0, 1, output is 1. For 1, 0, output is 1. For 1, 1, output is 0. Now, let us assume this B, you concentrate on the B number, it's B. So when it is 0 here, whatever the input is there here, the first one, The same has come here at the output side. Then it is 0. Same thing here also you can observe. Here it is 0, right? So on the first port, that is the first number, is 1 here. So the same 1 is seen on the output side here. But when you look at this second number, you look at this second number, when it is 1, the first number, whatever is there, the complement of that is coming at the output side. So first number is 0. The complement of that 0 is 1. Observe this case where your second number B is 1 and the first number is 1. So this 1 is complemented at the output side. So it means what? If you take the XOR gate and one input, if you are fixing to 1, then whatever the number you give here, this A may be 0 or A may be 1, you will get the complement of that. Is it not? That is what you. One input we are fixing. This is 1 and this is 1. This one input we are fixing. So now on A, let us say you have 0, then complement of that 0 is 1. On A, let us say you have 1, then the complement of that 1 is 0. So that's why it is A1. So the conclusion is XOR gate is used as a complementer. So with this idea, what we can do is we can build a circuit here. 1 bit full adder. This is 1 bit full adder. And same you take again 4 times because it's a 4 bit. Now you put this one here inside the box and you put here one XOR gate. Same here also take one XOR gate. Same here also you take one XOR gate. Same here one XOR gate. Connect this XOR gate to this 1 bit full adder to the second bit here, because full adder is going to take here 1, that is one input here B, another input here A, and one input is C in. So let's give here B 0. So we are giving here B 0 and here A 0. And here this A0 needs to be given there. Just a minute. Here is a correction. We give B0 only here and here B1 and here B2 and here B3. Another number we are going to give directly here, A0, and this is A1. And here it is A2. And here it is A3. Now, if it is an adder circuit, earlier we have done 4-bit triple carry adder, right? So wherein this first C in will not be there. So in this case, let us call this a C instead of C in. This is a mode. So for circuit to be like an adder circuit, if mode is 0, this mode is 0. This mode let us connect here for every second input of this XOR gate is going to this mode. Second input to this XOR gate is a mode bit. So when mode is 0, so here your XOR gate is taking one mode. One is a mode line. The other is your B0, B1, and then B2, and then B3. Here it is B0, and this is your B1, and here your B2, and here your B3. So when this is 0, earlier we have seen this, truth table, 0, 0. So whatever, when it is 0, one input is 0, whatever this, the other input is, same will appear here on the output side. If it is 0, 1, sorry, 1, 0. This second input is fixed 0. So this whatever input is there on the another input line, the same input will appear on the output here. That is 1. Okay. So it means there is no, it is not complementing, right? So it means what? When mode is 0, here you will get, if it is B0, B0 you will get. If it is B1, you will get B1. If it is B2, you will get B2. If it is B3, you will get B3. Now, if mode is 1, so it means what? Again, this can be second, one input line can have 0 or 1, but the other is fixed to 1, let us say. Now, this input is complemented here. You will get 1 here. And this input is complemented, you will get 0. This is the truth table, right, of XOR gate. So it means what? When mode is 1, then you will get B0 bar, B1 bar, B2 bar, and then B3. So based on your mode here that is given, you will get here either your B0 directly or B0 bar here, or you will get B1 directly or B1 bar. Here you will get B2 or B2 bar. Here you will get B3 or B3 bar, which is coming from this XOR gate. Yes. Now, when it is mode 0, it is like adder circuit. It's behaving like an adder circuit. Whatever you are giving A here, this A0, A1, A2, A3, that is nothing but your A. A size is 4-bit. And you have got this B0, B1, B2, B3, that is this B. B size is 4-bit. So they have been added here. Okay. When mode is 1, now what happens here? Mode is connected to all of these XOR gates, right? Just now we discussed here. Now we are not going to get B0. We are going to get B0 bar, then B1 bar, then B2 bar, then B3 bar. Now what you are going to do here is, you are going to add with this 4-bit of A, complemented version of this B, that is B bar. See, B0 bar, B1 bar, B2 bar, B3 bar, nothing but all 4 bits been complemented here. So that's why that is B bar. Now, what more here? This plus 1. This 1 is getting added here, right? This is plus 1. So what is this basically? This is nothing but a subtraction, right? Earlier we discussed in this video recording only. That is when A minus B we have to perform. So what we do? A plus complement of this B bar plus 1, that is 2's complement. So that will give the difference between this A and B. That is nothing but a subtractor circuit. So like that, this circuit is going to behave like a adder cum subtractor. When mode is 0, it is behaving like a adder circuit. When mode is 1, it is behaving like a subtractor circuit. So from this diagram, what is that we are understanding? We have to develop one bit full adder, and 4 times we have to instantiate 1, 2, 3, 4. 4 times we have to instantiate that 1 bit full adder. And then we have to use 4 this XOR gates. And this XOR gate will have one input as a B0 and another input as a mode. Okay. All these XOR gates will have one input, your B bit. B has got 4 bits, right? B is a 4-bit vector. So it has got total 4 bits like BC, B3, MSB, then B2, then B1, then B0. So one XOR gate will take 1 bit of B and the other input will be mode bit. So this 1 bit full adder is going to take the output of this XOR gate. If you look at this here, this is the output of XOR gate. Output of XOR gate. So your 4-bit, your 1 bit full adder is going to take one input directly from the A. The other input is from the XOR gate. Okay. So refer this, at this timestamp, you come back and refer how, this circuit is built if you have doubt. Okay. We will develop the code now for this. So to develop the code, you have to go to this model sim. Just double click this icon. So once it comes like this, then we close this one. Otherwise, this I will hide. So now I'm just closing this one and I'll go to File, New. Here is the project. And existing project, we have to close this one. That is what this prompt is. Close the existing project. And for the new project, give the name adder underscore come underscore sub sub underscore 4-bit. So this is adder underscore come underscore sub underscore 4-bit. And then this project location, observe carefully. Otherwise, if you do not pay attention here, you will make mistakes. So project location, browse this one. Go to some location where you want your project to be. I want my project on desktop. I have created one folder already on the desktop, that is lab demos. So inside that folder, I am creating another folder, new folder. This new folder I am naming as a adder cum sub. Without spaces, we have to give this one name. Adder cum sub. Select that folder. So that folder is what been added here for the project location. And the other two, you do not change. Keep them as it is. Click OK. So once that is done, close this one. Here, go to File, New, Source, Verilog. So here what we have to develop? We have to develop first 1 bit full adder. So module. Previously also we have developed this one bit full adder. It has got A, comma, B, comma, C in inputs and some comma CO output. Here it is input A, comma, B, comma, C in. So that is input. These variables are A, B, C in. These variables belongs to input type. Input here, this input is a keyword. Now output is a keyword here. Sum and CO variables belongs to that output type. Now here I am going to write in data flow level modeling, assign sum equal to A XOR B XOR, this is B, then XOR, then C in. So that is the Boolean expression. Straight away, I just used that Boolean expression of a full adder. This is the operator for the XOR operation. Now assign CO for carry out. The Boolean expression is A ampersand B, and then I have to OR that one, that is this vertical bar, or this is also called pi. Then open the parenthesis again, A ampersand C in, and then again vertical bar, that is for OR operation. This vertical bar is for OR operation, and this ampersand is for AND operation. So here B ampersand C in, and then terminate with a semicolon. So end module. This is one bit full adder. So save this file, click on save, and here only title you have to change. Okay, so that is FA. In my case, it is the FA. In your case also it is FA. Give relevant name. FA is the only relevant name. Full adder. Dot V. Save this. Next, what is required is that adder cum subtractor. So for that, go to file again, new, source, Verilog. Here, module, adder cum sub 4-bit. That is the name of the module. Adder cum sub 4-bit. Open the parenthesis. This module has got inputs A, comma B, two inputs. And instead of calling sum and difference, let us call it as a result. Let us call it as a result. So, and we need additional bit that is control signal mode. So just now we discussed here this one here. So this has got A, B primary inputs, mode one primary input, A, B are primary inputs, and the result that comes from this, this is your result. Okay, this is your result here. So this is the result of 0. And the carry generated is given to the next stage. So let us call this as C1. C1 is not a primary input. Now, from this stage, you will get the result. That is result of 1. And the carry generated will go to the next stage. That is C2. Now, this is giving one sum or difference. That is your result of 2. And the carry generated will be going to the next stage. Here, what we get is 1 is the result of 3. And this carry out or borrow that comes here, we are calling it as a result of 4. Okay. Hope this is clear. If it is not clear, watch again. This portion you come back and watch again. So instead of calling sum 0, sum 1, sum 2, sum 3, CO or difference 0, difference 1, difference 2, difference 3, and the borrow, what we are calling here result of 0, result of 1, result of 2, result of 3, and this finally carry out or borrow out is what here this is your result of 4. Okay. So with that, now AB mode result. So here now the type declaration input this A and B of size 4 bit. So A comma B, and then input mode here. Then output. This size is, look at this one here. 0, 1, 2, 3, 4. Total 5 bits, right? 0 to 4 means total 5 bits. So how to declare here in Verilog that 4 bits? Here we put 4. This is some not corresponding, just a minute. Here, total 5 bits, right? So 4 colon 0. That is your result. 4 colon 0. So now what we have to do, we have to first use this XOR gate. So XOR gate output, if you look at this one here, this one, let us call this output of this one here is Y1 or Y0, and this gate output is Y1, and this gate output is Y2, and this gate output is Y3. So here, just a minute. So this XOR, and first XOR gate output is Y0, and it is going to take 2 inputs, right? So one input is P of 0, and the other input is mode. So this file I will save first. Case if I, so let's give the name adder cum sub 4 bit 4 bit adder cum sub 4 bit. Save it, and here semicolon. So just copy this. Paste it here. Total 4 XOR gates are required. So this output is Y1, and this output is Y2, this output is Y3, and this input is B of 1, and this is B of 2, this is B of 3. So, and the other is fixed, that is mode. And then we instantiate the full adder. So this full adder, we have to instantiate 4 times. Copy this here 4 times. Paste 1, 2, 3, 4. And here, user-defined module name must have instantiation name. Instance 1, instance 2, instance 3, this is instance 4. So what you pass here is, one input is A of 0, and here this is A of 1 for the second instance of the full adder, third instance A of 2, fourth instance A of 3. And this one, instead of B here, we pass Y0, Y0, and here Y2, and here Y3. This is Y1, Y2, this is Y3. Now the mode is only for the first instance of the full adder. Second one will be getting the carry from this one. That is this uh, carry here. I kept C1 here. And this one is result of 0. Result of 0. First instance is going to take A of 0, Y0, this Y0, mode, and result of 0 is output. And the carry generated is C1. This C1 is going as the input to the next stage. So then this one is result. This is a result of 1 here. And this one is C2. Second stage is generating carry C2. Next is this C2 is coming as an input here. And this is result of, and this stage is producing carry C3. And the last stage is taking that C3. And this is producing a result of 3. And this is, instead of calling CO or borrow out, this is your result of 4. All right. So, and then finally, and so this one is exactly, if you look at this one here, so this is result of 0, and this C1 is going to the next stage. This C1 is going here to the next stage. And then this is result of 1, this C2 is going to the next stage. This is result of 2, then C3 is going to the next stage. Then here it is result of 3, and then instead of carry out or borrow out, this is result of 4. So go to the save, click on save. So this one you have completed. Now what is required is test bench is required. So to do the test bench here, we go to file, new, source, Verilog. Here we have to write the test bench. So to write the test bench, here backport, time, scale, 1ns/1ps, and then module tb underscore adder. This is addercumsub 4-bit. And then go to this file, copy, these things. From here, I'm copying from adder to this, all this till output. I will tell why from there I have copied. This one anyway, I have to instantiate, right? So just cut this from here and put down here. And this input will become reg. And this input also will become reg. And this output will become wire. And this, I have to instantiate the module that I wanted to test. So module name space, some instantiation name, that is DUT, that is design under test. And then these variables are intact, meaning the way they are in a position, same way you have to keep in test bench also. So that is called positional mapping. Okay. So here now initial begin. So here for display purpose, several examples I gave in the previous recordings. So that you can follow here, $monitor. But now instead of writing that display, what I'm going to do is just writing the inputs that I wanted to apply. So I apply here using this loop, that is repeat loop. Five values I will take for addition, five values for subtraction. So repeat five. Mode I'm setting here. Mode for addition, to do the addition, mode is set to 0. Already discussed. What's that in case if you have doubt? In this recording only, you just go to the previous timestamp and watch why mode 0 is required for addition. In case if you have missed that discussion. Now here, I have to generate A, that I am generating random values. How I generate random values? Using U random dollar U random. That is system function $u unsigned random is a system function. $u random is a system function. It returns some random values, unsigned integers. And then modulus, since it is going to take total 4 possible, total 4 bits means total 0 to 15. So total 16 possible cases. So if I divide by 16, then the remainder will fall. This is the modulus. This is for remainder. If you use the division operator, then that is for quotient. Here, this is the division operator. That is for quotient. So I am taking the remainder. So it will produce anywhere that remainder between 0 to 15. So same thing I copy and paste it for P also. Here P. And then here semicolon, you have to end any statement with a semicolon. And then with some delay. This delay also discussed previously, like this loop when it enters here, all these are happening at 0 simulation time. Then we give some 5 time unit delay. Then this loop will continue. At that 5, again, this values will be applicable. Again, 5 time unit delay, like that. So total 5 possible cases it is going to produce. Now what I do is I just copy this repeat loop. Copy and produce it here. This time I make this as a 1. Okay. So this is for subtraction. This is for subtraction. And this is for addition. Now, this begin end is done. This begin end is done. This begin requires end here. And then finally end module. Okay. So all is done here. Save this file. This is TB. TB underscore adder sub 4 bit. Dot V you do not touch, leave as it is, this dot V. Only file title you have to edit. Save this one. Now here to this project, you have to add them. Right click, add to project, existing file, browse, then select these 3 files. Open. And then click OK. So now these files being added to the project. Now go to compile all. So wait for the tick. So all 3 been tick mark has come. So that is successful, successful, successful. Now go to simulate. Let us close this one. Start simulation. Now locate the work folder. Here it is work folder. There's a plus sign. Expand that one. Locate your test bench module name. This is test bench module name. Select that. Click OK. Now in the console, things will not come here because I did not write the dollar monitor. So what I had to do, select this, right click and add wave. So this, variables will be added to waveform window. Now here, this is required to change from P to N, then run. Here, what you have to do is, you just click on this zoom full. All values are seen here. We can create a space. See the cursor shape, how it is changing. Here it is this. This is the shape. The moment when I bring here, it is changing this way. There you left click, hold it and drag like this to create the space here. Now you can zoom little bit here by clicking here and use this one here to drag and left and right like this. So anywhere you just click, corresponding to that values can be seen here. A value is this, B value is this. So if you take pen and paper and if you add and see that this is your result. Mode is 0 means it is performing addition. So when mode is 1 like this, here it is performing the subtraction. Let us see this example here. One example, what is this value? So here we have here we have 1, 0, 1, 0. And here we have B, 0, 1, 0, 0. Now if you subtract here, this is 0, this is 1, 0 minus 1. Difference is 1 and the borrow is 1. So 1 minus 1, 0. So this is totally 0. We're supposed to be getting this one here, 0, 1, 1. 0, 1, 1, 0. This is the difference. And this borrow here, if you look at this one here, that is this one. So since let's do this way, 2's complement. Let me remove this one. Again, I am writing down. Mode is 1. So mode is 1 means I have to do like this. A, B bar plus. This is what I actually require to do. So what is my A? 1, 0, 1, 0. What is my B here? B is 0, 1, 0, 0. So I have to take the 2's complement of that. That is this 0, 1, 0, 0. How do I take the 2's complement? B bar first. B bar means 1, 1, 0, 1. And then this plus 1 is this plus 1 here. So now 0 plus 1. Sum is 1. There is no carry generated. 1 plus 1. Sum is 0. Carry is 1. Now 1 plus 1. Carry out is 1. Sum is 0. 0 plus 1. This is 1. Now here 1 plus 0, 1. This 1 plus 0, 1. Now this last one. 1 plus 1. That is 0. Carry is generated. 1 plus 1. Carry is generated. So that carry is this. So now I got this as a result. So So 0, 1, 1, 0. This you can note here 0, 1, 1, 0, and this carry 1. This is the last one, this carry 1. So that result is correct. So like that, at any timestamp, you can go and you can observe. So going to another timestamp like this, same way the way I exercised. So you have to exercise this one and you have to justify. Again, I am repeating, in external exam, you cannot say that this is my output, something has come so. You have to justify the way I have given this justification. See, sir, this is at this timestamp, I have mode bit 1, and my A is this, my B is this. So I'm supposed to be doing the subtraction. So like that, you have to explain and justify that this result is correct. Okay. Simply saying some output has come, sir, just check. What is this? That is not the way. Okay. So kindly practice this, watch this, pause this video, and then if you have any doubts, reach me out. So in this code, I did not write that dollar monitor. Because of that, here in the console, you are not seeing the output. So you have to write that dollar monitor also. So to write the dollar monitor, I have given earlier in the past video how to write in this initial after begin. So you have to write here the dollar monitor, dollar monitor, open the parenthesis, inside the parenthesis, double quote, at the rate, time, and then here this percentage G, that is for time format specifier. NS is for our reference, that is in nanoseconds. Now I wanted to print A value in binary format. So percentage B is a format specifier. Then B value, that also I wanted to display in binary. That is percentage B is a format specifier. And then mode. So mode in percentage B, that is binary. You can keep uppercase also, no problem that way. Next, result. So result is also in binary format. Now, corresponding to these, whatever you have written inside this percentage G, percentage B, so many variables we have to get. So for percentage G, corresponding thing is this dollar time, that is system function. Now for this B, we have this A, B mode result only. So what I will do is just copy this and I will paste it here. And then close the parenthesis and terminate with a semicolon. And then save this file. Now you again have to compile because you have added this new statement, right? You have to compile. So compile all. See this under project here. Again, all ticks are coming here and no error here in the console window. Now you go to this simulate, start simulation. So again, as I told, locate where your work folder is. There is a plus sign, expand that. Go to your test bench module name and click OK. Once this is done, if you want to see in the waveform, then this procedure, right click, add wave. So that will add to this waveform window. But we wanted to display in the console means this dollar monitor is required. Okay. So now run this one. If here P, then change that P to N. Okay. Then run this. So now you can see in the console like this. So wherever mode 0, then it is going to add A plus B. Wherever mode is 1, then this is going to subtract A minus B. Okay. So how to verify this? I just demonstrated earlier. So we'll go to the previous timestamp and see how I justified my output. So in similar way, you also have to justify in external X. Okay. So that completes this experiment. If you have any doubts, post them in comment section or make a direct phone call. Okay. Right. Thank you.